Okay, so welcome to the solving session for this course, Fundamentals of Electronic Device Fabrication, which is being taught by Professor Parasuraman Swaminathan from IIT Madras. So he is a professor in the Department of Metallurgy and Materials Engineering at IIT Madras. So the course plan for this course is for the first week, which were for which the videos were shared last week. It was about introduction overview of semiconductor device fabrication, where he has shared videos about the history of semiconductor devices and transistors, how silicon wafers are made, and overview of the IC fabrication. So, and the videos shared this week, that is week 2, are for fabrication operations, that is oxidation, doping and lithography, which are part of IC fabrication steps. Detailed 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 topics on these. Then next week, videos will be shared about etching and growth and process evaluation. And the final week will be about process yields, clean room design, and IC logical packaging. So my session is every Tuesday 6 to 8 p.m. and you all know my Google Meet link. A little detail about me. My name is Mayan Goel and I am a research scholar in the Department of Electrical Engineering at IIT Bombay. My research is on 2D materials. So a quick recap for the first week that of this course, that is introduction and overview of semiconductor fabrication. The first part is integrated circuit history, which is about Moore's law, diodes and triodes, and then overview of IC fabrication, that is how silicon wafers are made from the most abundant silicon source, that is sand. So first step is submerged arc electrode process, which converts silica to and metallurgical grade silicon. Then Simon's process converts metallurgical grade silicon to electrical grade silicon. Then we have Chavorsky and Floatzone techniques, which are used to convert polycrystalline electronic grade silicon to single crystal ingots, and then these ingots are sliced into wafers. Next, there was an overview on IC fabrication on these wafers, where we have learned about the following fabrication operations: layering, doping, patterning, and heat treatments. Let's look at the summary PPT shared by Professor. Yes, so the first is the integrated circuit history, where you have vacuum tube diodes and triodes. You have an vacuum glass tube in which you have an anode sheets, and in between you have a cathode with a heated cathode. Diodes are used for rectifying operations, and then in triode there is a grid between the cathode and the anode, and triodes are the precursor to precursors to transistors, where you can perform operations such as amplification and switching. These are the cross-section views for vacuum tube diode and vacuum tube triode. And this is the cross-section view of a modern day transistor, which are made over a single silicon substrate. Then this is our Moore's law, which was given the Moore, which states that the number of transistors on a chip doubles every 2 years. It was later changed to 5x every 2 years, and it was valid. It was, as you can see, it was valid up till 2018, 2020, and now it's kind of slowing down. So, as you can see now, when the first transistors were made in 1970, they were around 2,000, 3,000 transistors on a single 1 millimeter square of wafer, 1 inch over 1 inch square of wafer, and in 2018 you have 10 billion more than 10 billion transistors on a same area. Well, these are the wafer sizes that are being used from in 1970 we used 50 mm square, and now we are the industry is using 300 mm square wafers. There are wafers generated OEM above 300 mm square diameters, but right now the industry standard is 300 mm square. Similarly, these are interconnects which are used to connect contacts between different layers. And right now there are 11 interconnect layers standard in the industry. Here you can see there are two interconnect levels. One is between silicon and M1, and the other is between M1 and M2. Then you studied the overview of IC fabrication, which typically consists of 5 steps. First is materials preparation, where sand is converted to polycrystalline silicon, where sand is first converted to silica quartz, then from quartz it is converted to mechanical grade silicon, and from metallurgical grade silicon, and from metallurgical grade silicon it is converted to electronic grade silicon, which is polycrystalline with impurities in parts per million or billion. Then second is crystal growth and wafer preparation, where polycrystalline silicon is converted to single crystal ingots using Shavarsky and Frozen techniques, and then these are sliced into single crystal wafers. Third step is wafer fabrication and sort, where integrated circuits are fabricated over the wafers, and the dies are then cut, and then in fourth step they are packaged into devices, and then final step is electrical testing of these packaged devices. So now we start with silicon wafer manufacturing. So the starting material is quartz, which is SiO2. Quartz is reacted with carbon. In the first stage, quartz is reacted with carbon, and we produce silicon monoxide. This silicon monoxide is then further reacted with carbon with silicon oxide further reacted with carbon to produce silicon carbide, and then silicon carbide is reacted with silicon oxide to produce molten silicon, which is then taken out, and this molten silicon is called metallurgical grade silicon because it contains a lot of impurities. It is only 98% pure. Then in a fluidized bed reactor, the metallurgical grade silicon is converted to hydrochlorides, and then silicon trichloride is taken into this chamber where it is reacted with HCl, and it is reacted with hydrogen to produce silicon and HCl, and this process is repeated till we get a good amount of silicon, pure silicon, which is, this silicon is called electronic grade silicon, and it contains impurities in parts per billion, where NGS was only 98% pure. And then next step is converting it to single crystal using either Chomsky method or float zone method. In Chomsky method, we have a rotating chuck with a seed crystal attached to it. The seed crystal is chosen based on the orientation that we want, surface orientation that we want. Typically, silicon wafers are used in two orientations, 100 and 111. 100 and 111 represent the Miller indice of the surface plane of the wafer. So seed crystal is a small piece of crystalline silicon that is attached to a rotating chuck, and this molten silicon is the electronic grade silicon, and then the seed crystal is slowly pulled away from the molten silicon, and you can see here is the seed crystal, and slowly pulls away from the molten silicon, and as you go away from the molten silicon, the molten silicon attached to the seed crystal crystallizes according to in the same orientation as the seed crystal, and that is how we get this inlet. In float zone method, a polysilicon rod is attached between two fixed chucks, and on one side a seed crystal is attached to the polycrystalline rod dependent on the orientation that we want, and these are heated RF coils which create a floating zone in the polycrystalline rod. These RF coils move away from the seed crystal, and as the molten silicon is solidifies, it crystallizes in the same orientation as seed crystal, and but float zone method is preferred over Chomsky method because float zone method gives less impurities compared to Chomsky method, because here the silicon rod is not in contact with any material. Here the molten silicon is in contact with the furnace and can take impurities from the furnace, but here the molten silicon is not in contact with anything, hence it is much more pure than Chomsky method, but due to limitations of the molten silicon away, being present in the middle, there is this heating, due to heating differential created, there is a limitation on the diameter in float zone method. So this is usually used only for small wafers. Most of the silicon wafer manufacturing is done using Shavatsky method. Then the ingot is then placed between a diamond cutter and sliced into wafers, and then based on the orientation and the doping of wafers generated, a flat is grinded on the sides of wafers for identification and sorting. If the wafer is P-type and orientation 111, only one primary flat is grinded. In case of N-type 111, apart from the primary grind, the secondary flat is grinded at a 45-degree angle. In case of P-type 100, the secondary flat is at 90 degrees to the primary flat, and N-type 100, the secondary flat is at 180 degrees to the P-type flat, to the primary flat. Next is the wafer fabrication, which consists mainly of four operations: layering, doping, patterning, and heat treatment. Layering is when a layer of a material is either grown on this wafer or deposited on the wafer. Like in oxidation, the SiO2 is grown on the silicon wafer. That means the silicon itself is converted into SiO2. Nothing is deposited from outside. In deposition, a material is deposited over the wafer, such as metals like aluminium, or even polysilicon is deposited on the wafers. In doping, ion implantation or thermal diffusion is done of boron, phosphorus, or arsenic to create regions of doping other than the primary doping of the silicon. Like in this case, you have a P-type silicon, and in which you have a N-type doping belts created. The plus denotes that it is highly N-doped. Then there is patterning, which involves lithography, which is used when you want only a certain region of the wafer to be exposed to the other operation, layering, doping, or any other operation. So using lithography, you can mask a pattern on the wafer, and mask the pattern on a wafer, and then perform other operations, and this way you get these regions, separated regions in your wafer. And the other operation is heat treatment, where the wafer is heated to a high temperature to either change its physical properties or properties of deposited layers. And in an industry, these patterns are repeated in forms of squares, so that in a single wafer you get hundreds of same ICs, which are then cut into dies, and these are test dies, which are then cut into chips, and these chips are then packaged into devices. Now, why we want to use larger and larger wafer? Because since the dies are square and the wafer is circular, we get edge chips which are not complete ICs and have to be discarded. So the larger the ratio between the diameter to the dice die side length, the lesser will be the edge chip percentage. That is why we have larger wafers in use. This is an overview of a MOSFET fabrication where you have the starting wafer either P-type or N-type. Then a field oxide is grown onto this wafer, and here you can see a pattern is a mask is made and then gate oxide is formed and the rest of the oxide is removed. Then we have polysilicon deposition, and after that mask source, after that it is again masked, it is again patterned, and for sourcing contacts polysilicon and gate oxide are removed from both sides, and these regions are then doped accordingly, and then metal is deposited. These are the deoxide and metal is deposited. So you have a metal connecting to your source, metal connecting to your drain, and metal connecting to your polysilicon gate. Now we will do some practice questions which is similar to your assignments. We can't do assignment questions that you have to do on yourself, but we can do questions later similar to assignment. So, hello. So first question, Moore's law states that the number of transistors per square inch doubles in every generation of an IC. So now consider an Intel Pentium processor that is based on 65 nanometer technology. Using Moore's law, what is the next generation? What will the nanometer technology used in the next generation of processor? 65 nanometer, 45 nanometer, 32 nanometer, 22 nanometer. Can one of you answer this question? Why? How do you get that? So the question is, in the question it says doubles per square area, and you are halving length. So if you half length, then area will be 1/4. So the correct answer would be 45 because you reduce the length by root 2 so that area reduces by half. You got that? If you reduce the length by root 2, then the area will be half. So you will have the same number of transistors. Then you will have the same number of transistors in half the area. So for equal area, you will have double the number of transistors. So the correct answer for this will be 45 nanometer. Okay. Now, second question. Which of the following components is not part of a vacuum tube diode? Anode sheath, cathode, grid, or glass tube? We just summarize this. Can anyone answer? You are saying it's anode sheath. And if it was, instead of diode, it was triode. The correct answer is C, grid. Because grid is present in a triode, not in a diode. All the other three components are present in both diode and triode. Only the grid is missing in diode and present in triode, and it is used to modulate the current between anode and cathode, hence acting as a transistor. Third question. The Siemens process converts what? Silica to MGS, EGS to single crystal ingot, MGS to EGS, or NGS to single crystal ingot. Yes, yes, it is. It converts metallurgical grade silicon to electronic grade silicon. Now, similar question. So you have this equation 2SiHCl3 plus 2H2 gaseous gives 2Si solid plus 6HCl gaseous. Which of these processes does this equation correspond to? Submerged at electrode process, Siemens process, float zone technique, or Shavatsky-Grove technique? What is submerged at electrode process, you know? Yes, but the metallurgy grade that we get directly from arc electrode is in molten state. Right. So here you are getting silicon in solid state. So the correct answer for this would be Simon's process, in which first the metallurgical grade silicon is converted to silicon chlorides, and then it is reacted with hydrogen to get polycrystalline silicon rods, which is your electronic grade silicon, and HCl as a gas. So next question. This is an equation for submerged electrode process. Can you figure out what is the missing here? SiC plus SiO2 gives silicon plus what plus carbon. SiO, that is your answer. SiO, and that is correct. And you don't even need to remember submerged electrode process to solve this equation. You can just compare these and do stoichiometric analysis and figure out the answer. So the fractional distillation process is to get, so when you have a fluidized bed reactor in which you react to metallurgical grade silicon to chlorine to get silicon chlorides. So you get SiCl4 and all other products. So when you use fractional distillation to remove all those, so that you are left with SiHCl3, and then it is reacted with H2 in that reactor to get silicon. That is what Siemens process actually is, or the whole process can also be called a Siemens process. So next question. Which of the following statements best describe the float zone technique? Conversion of EGS to single crystal ingot, conversion of NGS to EGS, conversion of SiO2 to MGS, conversion of MGS to single crystal ingot. EGS to single crystal ingot. And that is right. So, and similarly, Swarovski process also converts EGS to single crystal ingot. They are just two different techniques to get the same result. And float zone, as I told, float zone is suited for only small wafers. For larger, if we use float zone in larger wafers, then due to differential heating zone at the molten silicon, you will get defects in the wafer. So the outside edge of the wafer will see higher temperatures compared to middle of the wafer. So when it crystallizes, you will experience defects in the wafers. Hence, it is only used for small wafers. Next is, which of the following represent the correct sequence of stage going from silica to single crystal wafer? Silica, EGS, MGS, single crystal ingot, single crystal wafer, silica, MGS, EGS, with and that is the correct answer. So you take silica, then you convert it to MGS in submerged arc electrode process. Then from NGS to EGS in Simon's process. Then the EGS that you get is polycrystalline in nature, and we convert it to single crystal ingot using Shavatsky-Flournoy method, and then they are sliced it into single crystal wafers. So we just studied this. A wafer has two flats which are at 180 degree to each other. What is the type of wafer? P111, N111, P100 or N100? N110, N100, that is correct. So in P111, you don't have a secondary flat, you only have one flat. In N111, the flats are at 45 degree. In P100, the flats are at 90 degree. And in N100, flats are at 180 degrees. So by just looking at the wafer, you can tell the doping and the orientation of the wafer. We don't need to even measure the resistivity of the wafer. Next question. What is the first step in MOSFET fabrication? Doping, lithography, etching or oxidation? Yes. The first step is oxidation, where you grow the oxide layer on the silicon wafer, and then it is patterned to get source and drain regions. Okay, this we haven't studied in the summary. Which of the following is synonymous to planarization process? Etching, oxidation, nitridation or chemical mechanical polishing? Yes. So, chemical mechanical polishing (CMP), it is used to achieve planarization. In this, the wafer is put in a slurry. Slurry is basically molten SiO2 in a sodium hydroxide, and which cuts through the silicon, and also it is, so that is the chemical polishing, and also there is mechanical polishing using a scrubber. So hence it's called chemical mechanical polishing, and it is done in the beginning itself, where when the wafers are sliced, they would be very dull. So we use chemical mechanical polishing to polish either one side of the wafer or both sides of the wafers, which are called single side polished and double side polished. Usually, in most of the cases, we use single side polished wafers, and after multiple fabrication processes, we find that the wafers lose the. So since we are depositing films, we are growing layers. So all these causes a deep planarization. All these causes changes in the wafer height. So planarization is often required in between multiple steps of fabrication to keep the wafer plane. Next is, which of the following is an example of heat treatment process? And yes. So actually there are two TAs for this course, and we have independently selected a slot for the session. So mostly the similar part they will also will be teaching, like they are not exactly related or exclusive. They are teaching on their own. I am teaching on my own. Uh, it is not in my hands now. You can request the professor maybe. Okay. Which of the following is an example of heat treatment process? Ion implantation of dopants, silicide formation after metal deposition, spin coating of the photoresist, electroplating of metal interconnects. Option D, electroplating of metal interconnects. Silicide formation. And why do you do heat treatment in that process? You are partially correct. So the answer is silicide formation after metal deposition, because after you deposit the metal and then at high temperature the metal reacts to the silicon to make silicide. But even in other cases, like an ion implantation of dopants, after the ion implantation is done, you anneal the vapor, you anneal at high temperature, because to fix, when you do ion implantation of dopants, the dopants are getting into the silicon vapor and they are destroying the crystal structure of the vapor. So to regain the crystal structure, you do annealing at high temperature. So ion implantation itself is not a heat treatment process, but it is followed by a heat treatment process, where silicide formation is done at high temperature after metal deposition. Hence, the correct answer is silicide formation. In spin coating, even spin coating, there is some heat treatment involved, but not at high temperature, and that heat treatment does not affect the vapor; it affects the photoresist. Similarly, after electroplating of metal interconnects, you might want to do annealing so that the metal interconnects are make good contact with your layers below. In some cases they are done, mostly not, but directly the answer would be silicide formation. So next question, the first monolithic IC used what for creating electrical connections? Copper wires, germanium, silicon, or evaporated aluminum? Evaporated aluminum. And do you know what is used in today's industry? Copper or copper wires? No, you use evaporated copper, not copper wires. So aluminum was used initially, and it was used for many years. Recently, recently it was found that aluminum was reacting with silicon and forming silicide, and that was reducing the lifetime of the devices that were made. So currently copper is being used for metallization, but there are barrier layers which does not allow copper to stick to silicon. They are separated so that copper does not react with silicon. Okay, these were the questions that I had prepared. If you have any questions, you can ask. At same time, Tuesday 6 to 8. So week two session will happen next week. You can post in discussion forum so others can also look what questions you have. Like so that if you have some question, others can also look at in the discussion forum. So if you send an email to me, then only I will know what questions you have. But if you ask me in a discussion forum, others can also know the questions. So it will help everyone. Yes, you can. Thank you.